Yes. Okay, so at Northwestern University, and you'll be speaking about the geological basis for intelligence. Thank you.
Thanks a lot. I would say I am down some sort of heard things. My voice will be a bit raspy. I want to thank the organizers a lot for inviting me. This is my first time at RLN, and I've really enjoyed the last couple of days. So I'll definitely not be my last time. So today I'm going to tell you about a story we've been developing in my group over the past few years, and it's really about evolution, and we all know that evolution is a natural selection of favorable traits, and in a given environment. Just like our LBM speakers, vertebrate life divides neatly into wet and dry varieties. So what I'm curious to explore with you over the next 30 minutes is, what is it about aquatic environments that favors certain kinds and disfavors other kinds of action control, and similarly for life on land? That's what I want to explore. I'm going to start with a little bit of motivation from some work I've done on vertebrate dynamics modeling, and just give some videos to build some intuition. Here's on the left is electric fish hunting in the dark. Water fleet. In the middle, we have a larval zebrafish hunting a single cell animal. And on the right, we have a dragonfly nymph hunting a larval zebrafish. So what I've done is I've frozen all of these movies at the frame at which the predator reacts to the prey, so our estimate as to when it detected the prey. This really tells you all you need to know about aquatic interactions that are dynamic, which is they typically are short range. They're occurring at less than a body length, and they occur very rapidly. So let's take a look at these videos. Electric fish is a passenger. I used to do that. Just scan its prey before it. And these are slowed down so that you can see them. But they're all near field interactions, right? But so what's the issue with this kind of action control is that it has to occur very fast, and being fast means you're pretty inflexible, and being inflexible means that you could be hacked. Your nervous system could be hacked by a smarter animal who wants to eat you. And so I want to show you this: a tentacle snake versus a fathead minnow. So tentacle snakes are secondarily aquatic. They evolved on land, and now they primarily live in water. And this animal has figured out to ripple its body from tail to head, which sends a pressure wave here. And all aquatic fish have this giant neuron in their brain that is in charge of escape and triggers an escape with 10 milliseconds delay. So that's about as fast as you can get in neural conduction delays. And so let's take a look at what happens here. So it's so stereotyped, the snake knows exactly where to put its mouth, right? So this is like some sort of acme of predatory success, right? You're able to, without lifting a finger, get sushi delivered, and you don't have to see anything with it. All right, so this does not take on the fathead minnow. This is something that we do as well, right? So you might remember this incident of analogy with George Bush, and something being thrown at George Bush, right? And of course, we can imagine the following delicious counterfactual that Nori, who honestly probably would like to be in cahoots with the journalist, is in cahoots, and exploits the fact that he knows that George Bush is going to be ducking shortly, and puts a premium on that, right? So you're predictable, whether or not you're a president or a fathead minnow, we all bow to the exigencies of having to act really rapidly, right? We have to do these rapid things and not do a lot of calculation. So back to this, this is a sort of dynamic behaviors in water that have to occur at short range, but we know that terrestrial predation, at least in some modes, occurs in something like this situation, where I've already trimmed off a whole bunch of stalking along here, so you don't get bored. And we'll just cut to the chase, as it were. Just take a look at how this big cat is exploiting the partial observability of land and timing its movements so that it's only going up when the animal's bringing its head down. That's not really fast, but we'll see what happens. I was waiting for that last. I'll put it there. I think you can imagine what happened. So, what does this fundamentally derive from? Well, the most obvious thing is something to do with air versus water. So we look out. Most of the stars we see with the naked eye are hundreds of light years away, and they've gone through about 60 miles of atmosphere. Yet we're able to get those photons, right? So air is basically transparent to light. However, water is not. We did a bunch of work some years ago looking at how ice changed pre-water to land transition 400 million years ago to water to land transition, and we found that ice tripled in size. But let's just focus on the ancestral ice size. This is gleaned from orbit data, which we can get from fossils. So we can do pretty accurate optical calculations of how far away we can spot a 30 centimeter black disk. And through the water model we think is most appropriate for what we think the development features went through, we're getting about 7 meters of protection range for that 30 centimeter black disk. Now, in perfectly clear water, that number gets to about 10 to 14 meters. And that perfectly clear water doesn't exist on the Earth. We're able to simulate it, but it's very short, okay? Whereas through air, that same eye, with a few corrections to the shape of the cornea, can go half a kilometer. Now, with the tripling of the eye size, which we saw in right after the waterland, well, during the waterland transition, we get a marginal increase in range through water, but almost a kilometer through air. So on net, going from this eye to this eye and changing medium, we get a million-fold increase in the total volume of visually accessible space. All right. This has profound impacts on the vertebrate brain. I think it's a very crude thing to look at, but well, before I do that, I'm actually going to show you this cartoon. First, showing you a typical visual scene underwater, blurry, maybe occasionally a predator or something. You've got a prey going through the space, intersects with a predator, and then this smaller cell fires off fast enough and escapes to live another day. On land, we have a totally different situation where, at least from this perspective, we're getting some very nice long sightlines. Of course, if you're in some clutter, you'll be getting short sightlines if you're in a rainforest. But the point is, you'll have a variability. You'll have both long and short. And so we can imagine a situation possible with a prey in this space where it could actually spot a couple of different trajectories that it can take in the future. And if it has the right neural circuitry to hold its motor outflow in advance while it evaluates the possible outcomes of these paths, it might pick the one that might be best, avoiding the predator and swimming through the pond. So that's the conceptual model. And if that model is roughly correct, it's utilizing this much larger volume of space and having to process a lot more information. And I just want to show you this data. I don't think it's appreciated enough about how brain sizes change during the waterland transition. And so we have goldfish brains. We have a whale shark that's 2,200 times the mass of a cat. Then we have a cat brain, right? And then here's a sheep brain, not known for their brilliance. Now, if you plot all of these brains, you'll see on a log plot, there's a pretty sizable gap. There's an order of magnitude increase in the size of endothermic brains over the biggest radiation, the most active predators over aquatic animals, minus the mammals that return to water, which you get in. So we can't, obviously, the paleontological stuff was based on looking at fossils, because eyes or orbits fossilized. We can't, behavior is a spatially temporally extended object that doesn't fossilize. It's really unfortunate. So we're going to have to do some modeling to try to get any clues here. And so what we're going to do, I'm going to show you modeling in a aquatic condition and a terrestrial condition, super simplified. It's really, I think, more of a thought experiment, possibly some motivating empirical work I'll show you later. So in an environment with no clutter, okay, let's vary visual range from 1 to 5 body lengths. The behavioral control mode from habit-based action selection to plan-based action selection, and if planning, how far ahead or how much planning is going on. All right, so here's our grid world. We've got our prey visual range, we've got our goal for the prey, and we have the predator roaming around slightly faster than the prey. The predator action control is very simple. It's just a reactive pursuit thing. Like imagine a reptile pursuing a deer, a Komodo dragon or something. Okay, so it's aggressively pursuing the prey with a little bit of randomness. And all right, and in the plan-based action selection mechanism, we're using partially observable Monte Carlo planning from Silver and Vaness, 2010, really dusty algorithm, but useful for our purposes. So what is that? It's MCTS, where the prey is imagining a whole series of moves and building a tree of possibilities with a variety of heuristics, VCV1 and so on, and picking the path to take after building that tree, and then executing that path that is most favorable. All right. So that's how we do planning in space. Of course, in the aquatic condition, we don't have obstacles. In the terrestrial condition, we do. But I'll get to that in a second. And let's see, anything else? No, that's good. So here's an example of planning with smaller trees versus bigger trees. We went up to 5,000 for seed simulated. All right, so the habit-based action selection mechanism is a really boring and kind of dumb algorithm, so I'll just give you the gist of it. You have a bag of successful trajectories in space. Let's suppose that we're talking about a condition, a visual range of 5, and suppose the predator spawns random. Suppose the predator spawns somewhere where the prey cannot see it. So in that case, we take all success paths where the predator spawned in a non-seen place. And then what we do is we select one with uniform probability. It happens, and in this case, hooray, the predator didn't get there. And so we await that particular path a little more, and we just do that every time, and we do this millions of times, and then get a probabilistic bag of trajectories. And if the predator spawns somewhere that the prey sees it, then we index these success paths by all success paths of the predator spawning in that particular position. Okay, so that's the gist of it. It's not all the details, but it's enough just to give you the flavor. And so here's what we find. Okay, so with as we vary the amount of planning at visual range 1, we get very low survival, less than 2%. Here's 10 here. And as we increase the visual range, unsurprisingly, we get better survival, and it also increases with in proportion to the amount of planning. But the important thing is, let me show you some of these trajectories. So visual range 1, lots of death, lots of very cool death, and then planning range 5, we get slightly less death. Now, one thing that's kind of interesting here, and we certainly didn't anticipate, is that the trajectories are what behavioral people call pigmentactic, following the walls. And it's such as a purita of anxiety of an animal. They use it in the pharmaceutical industry for deciding whether a drug is effective. So if it's effective, then an animal will hang out in the central area. If it's not effective, it will run along the wall. So we get pigmentaxis out of this, which we really didn't anticipate. And the important thing here actually is, though, if we look across visual ranges of survival rate, And we look at planning versus this algorithm I showed you for habit-based action selection, we get no difference, no statistically significant difference across the individual. So this is kind of interesting to us. We've gone on then to model terrestrial conditions. So now we add clutter and unlimited vision. So in the small grid world, that's up to 20 body lengths. And now we vary density of clutter. We have a way to do that randomly. And then we again vary habit based action control or plan. And if planning, how many states again? And here's just a note about how that works, right? So can't see, the prey can't see the predator there, now can. And the COMCP algorithm has a particle filter to account for release state modeling. Because once the predator is out of view, the only way for the prey to plan effectively is to have some sort of probabilistic model of where that predator will be. So that is given to it, it's not learned. So this is not very biological. But we're kind of interrogating what different ecologies can give us for sort of an index of how much planning needs to be. So we're not too worried about planning, we're learning quite well. So here's some different grid worlds with different levels of clutter, just so you have a sense of that. And here's our results. So at low levels of clutter, we get a survival rate which is not that different or statistically indistinguishable from habit. Similarly, at high levels of clutter, but in the mid-range clutter condition, we saw a big signal. Not only did survival rate go up significantly, it varied systematically with the amount of planning, up to this 5,000 states for example. So what's going on there? So let's take a look at some of these simulations. The low clutter conditions, just like the aquatic case, it's kind of stigmatactic and it's not surviving a whole lot. In your success paths are very inflexible or wall falling. In the high clutter condition, what happens there is that your survival is kind of a random chance of like where does the predator spawn. So with predator spawning around there, we get kind of this as a success path. But it's kind of a random thing. So it doesn't really help plan in that case. So that's why we think there's not much planning signal that. But in this mid-clutter condition, we see trajectories very commonly that include seemingly kind of devious for grid world strategies. So here's a prey, right? It's kind of luring the predator into this little closed area and then shooting out the side once the predator is close enough for it to see it, and sort of then it gets delayed because it loses track of it, and so on. So we see these kinds of pretty interesting or more interesting behaviors in the mid-clutter condition. And the success paths are layers, as you might expect from that video. So much more broadly across the environment. All right, so simulations, obviously, these are toy models. They need experimental support. And the grid world is too small for naturalistic experiments with real animals. So what I'm going to show you is a paradigm we built up over the last couple of years to test this experimentally. And I'll just forewarn you that what I'm going to show you is data that validate the method for the publication from last year. And we just finished last week our last mouse for the empirical test. So I don't have that data, but I'll show you the empirical data for the validation of the paradigm, which has some interesting nuggets in it. But I'll kind of go pretty quickly through that. Now, luckily, I was able, because I'm a fifth person, I was able to interest this guy, Dan Dombeck, who's a really outstanding neuroscientist who works on mice and in the hippocampus, which is obviously a pretty important putative structure for this behavior. And so we've been working over the past few years, and I want to call out Morgan again, who done some great work as a postdoc with David Reddish, who's leading my lab, and did a lot of the modeling you just saw. Gabby Link just some of the robotics you're going to see. So I've collected a lot of the data, and Chris collected the neuropixel data, and Armand a lot of the mechatronics that when the apparatus goes through. So here's the apparatus called Cell World. We have a start door and end door, automated doors, water awards, everything's automated wireless. The robot has, I'll tell you about the robot in a second, actually. And we have these obstacles that are magnetic and movable, and we have high-speed tanks. Okay, so here's the apparatus, and just to show you some different regimes. Okay, here's one outtake of the experiments. We thought when we first built the robot that having this orange black thing charged at you might be scary enough to not have to use anything in addition. But what in fact happened was that we built the first robot, I should say, rodent segue. So take a look. This is a first exposure of the mouse to the robot. And it's on the ride. Like this is the first exposure. It's clearly not intimidated by robots. So much for that, right? So we put a CO2 blaster on it, and that works much better. So you're going to see this arrow turn red when it blasts. This is again a naive mouse, the first exposure. And it's sort of, I'm surprised that it's starting to stop to look back. Like, I guess if you're going to get out on it, I don't know, but anyway, so after those exposures, those initial exposures, these animals seem to avoid the robot as if it were a predator. Of course, we don't know that it thinks it's a predator, but it certainly doesn't come close enough to be bitten, in case it did have a long. All right, so here's the task. We call it body day, the start door, end door. It's got to get through the space, evading the robot, and then it comes down the chute and returns for another water reward. These are water restricted animals. All right, so we have white noise generator, methanol moving the olfactory cues. And so I'm just going to show you a couple of behaviors that popped out pretty early on. So mice always learn this trick really rapidly. It's just amazing how fast they learn it. So it's dating-like behavior. So it sort of gets the robot's attention and doesn't run all the way back. It sort of goes halfway, come along, and then shoots over there so that it can now go to the north side, and it knows that it's not going to intersect the robot now. So every mouse we dealt with learned this within, I don't know, 10 trials or so. Pretty impressive. And another thing we really liked was the way it was leveraging partial observability, kind of like that big cat in space. So take a look at this run. Peak 1, peak 2, long peak, and reroute. So that kind of thing happens all the time. And we're really curious about those stoppages because this is essentially a good place for animals to be planted or doing something of that nature. So let me show you a video now of this interaction. But now we take our whole CP algorithm and we just use the belief state calculation so that we can see, kind of start to get an estimate of what the theory of mind of the mouse is with respect to the robot as it charges along. So the belief state model is incorporating a whole history of past observations to get a Bayesian estimate of the density or the probability, if you see, of where the robot is. And so you'll see at the first peak, the belief state collapses, and then you'll see it diffuse out again as the robot goes out of it. Okay, so we see the collapse, come back, and now the peak. All right, so it's clearly picking a path that avoids that reasonable space. So here's our validation data. All right, so not super interesting. So we're just we're coloring the trajectories. There's 6,000 of them here by velocity, and this is pre-robot introduction. This is post-robot introduction, and this is I'm sorry, not post-robot. This is robot with the robot, and this is post-robot. And you see quite a change in the diversity of trajectories there. We also looked at no obstacles, so this is starting to get to some of the empirical testing of does the complexity of the space really have big input on strategy, behavioral flexibility, planning, but that's as far as we've gone, as I said, until the data was spent. So open arena, but no threat, open arena with the robot. exactly impacted, just like our simulations. All right, so we just, here's a couple of crude measures, number of bundles, we bundle up the trajectories, and we look across experiment phases. We also looked at the mean distance between the trajectories that were not in bundles to the nearest bundle. And you see this sort of characteristic initial around 3, and then it goes up, more diverse with the introduction of the robot, then it really collapses after the robot is removed. And similarly, the distance to the nearest cluster starts off at that value, then goes up and then goes down significantly. So, but whether an action is plan-based or habit-based is clearly not something that's going to be fully determined just by looking at the behaviors. So we need to start to dig in a little bit beyond that. So as many of you know, there are two neural correlates of planning that we can begin to examine during the activity. So Chris and Dan put neural pixels in the animal, and I just want to tell you a little bit about, you probably already know this, but for those who don't, there's a part of the brain that's the campus that has this thing called the cognitive map, and it contains these cells that activate when the animal's in one particular part of the space. And so this is a cell that says, I'm in that part of this arena here. This is an arena is a scale bar. And if you look across cells, you can tile the space with these place fields, place cell fields. And then you can build a decoder to sort of just record from the brain and detect where the animal is in space. Okay? So decoder is normally reporting or often reporting where the animal actually is. And so exactly on top of each other. But what's really interesting is that sometimes it's not at the same place as the animal is. And so this is called non-local activity in the literature. And so that has been starting to emerge as sort of starting to, as for some time, been thought as a possible substrate for planning in the past. All right, so we're going to look at that. So I'm just going to show you first with some shanks in the brain that we do get place fields for the animal. And now I'm going to show you a video where we have the robot chasing the mouse around. Now this is slightly different task. We've modified it to get better coverage of the space. We have water converging ports here, indicated by triangles. Mouse doesn't know which one is on, so it's going to start looking for one. And you're going to see the actual mouse location here, and there's our decoder output is the pixelated thing that you see adjacent down here again as well. So take a look at it. So we want you to see what happens when the robot comes into view. So it's like it starts with the path that you can see, like it's going a little bit between these two locations, and eventually picks the one that you want to think would be wise place, right? So we're currently going through many terabytes of data like this for a publication, but I just wanted to give you a little sense of what the data currently looks like. So, in parallel with investigation of planning and spatially complex arenas with this robot adversary, we're also delving in into how the mouse might actually learn this task. And for that, so yeah, and I wanted to add that rapid emergence of baiting, etc., suggests that the mouse is quickly learning the dynamics of its adversary. So maybe there's an opportunity here for comparing how learning proceeds with what we find using a leading RL model. And so for this work, we collaborated with Bradley Staddy, who's a new professor at Northwestern. He's done some really great work on this problem. And I just want to highlight a couple of results. Here's the preprint that's been accepted ICML. So here is the same trajectories you saw, 6,000 or so, but now colored so that anything within 10% of the distance of the wall gets coded as blue as stigmatactic, as is possibly anxious trajectories, and the other ones are red. And so the real mouse following trajectories have wall following 70% of the time. And what we found with TDNPC2, which is a pretty modern state-of-the-art algorithm for RL is that there's no wall falling, 0% wall falling. So this is kind of an odd thing, and it's all about the way that this algorithm is harvesting reward prediction error, which tends to be, well, the analog would be death, obviously in the virtual form here. So here's one of the trajectories, and you can see that it gets captured, no problem. So what did we do? Well, so we have the agent knows nothing. The RL agent knows nothing of the potentially mortal threat that the robot perhaps represents, the mouse. And so maybe this gap could be bridged by giving RL a sense of danger of the mortal threat beyond large negative rewards, which we could try, but basically it prevents the mouse from moving because moving in space is all it's doing. So just so we modeled something akin to post-traumatic stress disorder, which is, as you know, repeated recall of traumatic experience by oversampling negative experiences from the replay buffer during training. Okay, so when we did that, and we also introduced a penalty term in the temporal difference target that's proportional to the Q value variance. And we found just empirically when we looked at the Q value variant that it seemed to be the places where the mouse was being cautious, and it seemed to correlate to lack of predictive efficacy. Okay, so we put a penalty on that, and so this is the algorithm that we now use for our testing. And I just want to show you one trajectory for a flavor of the caution that you can see in the resulting trajectory. So much more possibility. So here's the overall visitation density plot for this modified RL agent compared to TDMPC2. And compared to the mouse, it's still a lot less pigment active, but we had 21% overlap here, and now we get 86% overlap. So we still have a way to go to make this, I guess, you would be anxious as an RL agent before we get there, but we're our way there. All right, so last couple of slides. So planning is an early tetrapod innovation, possibly 250 million years ago with the onset of endotherapy. Then what we should share significant aspects of this trait with mice. Humans should be diverged 90 million years ago. So we put our task into VR. We have a scary ghost, and we have people running around in a space with more confidence than we have in the technology, getting those columns. We now are doing it in the indoor football field, so more space to the human participants. Anyway, so here's some, we started this effort some years ago. Some of you might have seen this 3 years ago. And then the company we were collaborating with, this VR company, went out of business. So we had to basically redevelop the whole technology system again ourselves. So that was a big cost. We finally finished that. We're going to start collecting data in the next few weeks. Last thing I want to show you is that if the hypothesis that terrestrial vision was key to the emergence of planning is correct, then this could arise in any animal with the appropriate visual apparatus and mid-flutter conditions. And so we began working on this species of a jumping spider that has really bizarrely high visual. Invertebrates in general have incredibly low, like a quarter of a cycle per degree, you have 60. This jumping spider we're looking at has the acuity of a pigeon, all right? So it can look at you, and it does when you're in the field. It looks at you and tracks you from quite some distance. It's a bit weird. So this animal engages in stalking sequences that last between 20 and 90 minutes. And so we did a field trip to Malaysia to look at this last summer. Here's a photo I took of one of them. You can see it's tiny, bizarrely, like big eyes. Here's a plot of acuity versus eye diameter. This guy's up here. Look at all the vertebrates it's kind of beating at, right? They're amazing. Anyway, I just by dumb luck happened to have my iPhone out, and we captured what is thought to be the first wild sequence of this animal. It took 40 minutes of me holding my cheekbone. It was really backbreaking, but I have a highlight reel. I'm happy to show people the 3-minute highlight reel. I can show people another time. But so just to end, the water to land transition in the Lake Devonian was also a habit plan transition in the action control menu of landowners, fueled by their million-fold increase in visual sensory volumes. Planting shines in the shade of the partial visibility of mid-cluttered terrestrial environments. And maybe this is a geological constraint on cognition. So, you know, and if Earth had been a water world, it seems likely that nothing interested in watching talks at RLDM would have been welcome. Apologies any pocket was in so I showed you some data from for validation of a new paradigm and test this idea with parallel comparison to humans and spiders. And I've shown you a bit of data where we think maybe traversing this gap between RL and biological learning may involve giving RL some respect for our mortality. Okay, so I'd be happy to take questions.